If you're an avid gamer, you've probably taken a few moments to appreciate some of your favorite aspects of your most beloved titles. Sometimes it's the graphics. Other times it's the music. And in some cases, it's the AI.
There's 3 of them, I think. Are they friendly?
All of these aspects have one thing in common. They're driven by a silent and powerful entity that has no face, no feelings, and no function other than to create some of the most brilliantly rendered virtual environments the world has ever seen. The engine. From Unreal to Havoc, these complex pieces of software are responsible for creating multi-billion-dollar international conglomerates that you may love or hate. But what exactly is a game engine? Why is it necessary? Where did the concept originate? That's what we're here to find out. Simply put, a game engine is a software development environment designed to allow anyone to build video games. Developers have been using these for decades to create games for consoles, PCs, and lately, even mobile devices. The primary functionality given in a game engine usually includes a rendering engine, sometimes called a renderer, for graphics, physics, audio, and so on. In some cases, they may even include support for cinematic implementations, as seen in movies like Solo, a Star Wars story. Typically, game engines offer a variety of development tools in addition to reusable and adaptable software components. Some game engines are so advanced and visually oriented that a person can actually create a game without ever having to write a single line of code. For example, the modern-day Unity engine. These very tools are usually provided in an IDE or integrated development environment to allow a streamlined developmental process. Game engine developers themselves attempt to pre-invent the wheel by creating software suites which include many elements a game developer may need to build a game. Most game engine suites provide facilities that ease development, such as the aforementioned graphics, sound, and physics functions. As a result of these engines being a core function of game development and offering out-of-the-box functionality, they are often called middleware. It is worth mentioning they also reduce costs and ambiguity in the process, all necessary to allow for success in such an industry. One key feature that keeps game developers coming back for more is what's called platform abstraction, or the ability to run the same game on multiple platforms, consoles included, with only some minor changes in the source code being applied. In some cases, a developer may want to create a custom engine and may do so by combining loosely connected middleware components. This can sometimes save costs over time. Additionally, developers strive for something called extensibility, or the ability to extend or modify their engine as industry demands change and increase in volume. Conversely, some game engines only allow for real-time 3D rendering capabilities. These engines solely rely on the developer to implement the rest of the desired functions mentioned a moment ago. These types of engines are often more name-specific, as they do not provide the seemingly universal and unlimited access to the developmental tools seen in Unreal or Unity. These are instead often called graphics engines, rendering engines, or simply 3D engines. As technology ages, the components of an engine may become outdated or insufficient for the requirements of a given project. Since the complexity of programming an entirely new engine may result in unforeseen delays, a development team may elect to update their existing engine with newer functionality or components, in some cases creating an entirely proprietary piece of software. In layman's terms, the rendering engine generates animated 3D graphics using mathematical processes. For example, rasterization, or the task of taking a simple shape and converting it into what is called a raster image, or a series of pixels, dots, or lines to then represent the aforementioned shape. There is also the process of ray tracing, which is a rendering technique that involves tracing the path of light projected onto an object as pixels, allowing for greater precision in virtual simulation. Instead of being programmed and compiled to be executed on the CPU or GPU directly, most rendering engines are built upon one or more multiple rendering APIs, or application programming interfaces. You may know some of them as Direct3D, OpenGL, and Vulkan. Before hardware-accelerated 3D graphics, software renderers were used. Software rendering is still used in some modeling tools or for still-rendered images when visual accuracy is valued over real-time performance or when the computer hardware simply does not meet the needs. Game engines can be written in any programming language like C++, C, or Java, though each language is structurally different and may provide varying levels of access to specific functions. In many cases, a scripting language like JavaScript gets added as a second layer to expedite the development. The audio engine is the component which consists of algorithms related to the loading, modifying, and output of the sound through the client's speaker system. At a minimum, it must be able to load, decompress, and play sound files. More advanced audio engines can calculate and produce things such as Doppler effects, echoes, and oscillation. The physics engine is designed to provide an approximation of certain physical systems such as collision detection, soft body dynamics, and fluid dynamics. More recently, there has been an uptick in the use of game engines to create fantastic worlds for cinematic viewing pleasure. When it comes to classifying physics engines, there are generally two categories: real-time and high precision. High-precision physics engines require more processing power to calculate very precise points in physical spaces and are usually used by scientists and in the creation of computer-animated movies. Real-time physics engines are more common in the interactive computing world as they use simplified calculations and are comparably decreased in accuracy to compute in time for the game or simulation to respond at an appropriate rate. Believe it or not, one of the first computers, known as ENIAC, was used as a very simple type of physics engine, aiding in military ballistics calculations and tabulating the results on paper for artillery commanders. Since then, physics engines have been commonly used on highly advanced supercomputers to perform computational fluid dynamics modeling. Due to the requirements of speed and high precision, special computer processors, known as vector processors, were developed to expedite the results. It is widely understood that in most computer games, speed and fluidity of the gameplay are more important than overall accuracy of the simulation. As a result, this created a demand for physics engines that produced results in real time, but minimally replicated real-world physics. In other words, creating a perceptually correct approximation. However, some game engines, such as Source, use physics in puzzles or in combat situations which require greater precision and accuracy. In the past, physically based character animation only used rigid body dynamics due to the speed and ease of calculation. However, modern games and movies are starting to utilize something called soft body physics. Soft body physics can also be used for particle effects, liquids, and cloth. Typically, most 3D objects in games are represented by two separate meshes or shapes. One of these meshes is the highly complex and detailed shape visible to the player in the game, such as a vase, for example. For the purpose of speed, a second simplified invisible mesh is used to represent the object in the physics engine so as to force it to treat the example vase as a simple cylinder. However, this would make it impossible to, for instance, insert a rod or fire a projectile through the handle holes on the vase. Because the physics engine model is based on the cylinder and is unaware of the handles. This simplified mesh, used for physics processing, is often referred to as the collision geometry. Within said geometry, there are typically two principles in play. A bounding box, which is the minimum or smallest bounding for a point that has been set in specified dimensions, or a concept known as a convex hull, which can be defined either as the intersection of all convex sets containing a given subset of a Euclidean space, or the set of all convex combinations of the points in that subset. For a more detailed look at these concepts, check the description below for some helpful links. Engines that use bounding boxes or bounding spheres as the final shape for collision detection are generally considered extremely simple. A bounding box is often used for broad phase collision detection to narrow down the number of possible collisions before the more expensive mesh-on-mesh collision detection is done in the narrow phase of collision detection. Another aspect of precision in discrete collision detection involves the frame rate, or the number of moments in time per second when physics is calculated. Each frame is treated as separate from all other frames, and the space between frames is typically not calculated. This is often why a low frame rate combined with a small, fast-moving object causes a situation where the object does not move smoothly through space, but instead seems to teleport from one point in space to the next as each frame is calculated. Additionally, projectiles moving at significantly high speeds will likely miss targets. Multiple techniques are used to overcome this flaw, such as Second Life's representation of projectiles as arrows with invisible trailing tails. Conversely, the continuous collision detection demonstrated in the Bullet or Havoc engines does not suffer this problem. On the other hand, an alternative to using bounding box-based rigid body physics systems is to use a finite element-based system. Essentially, the finite element method subdivides a large system into smaller, simpler parts that are called finite elements. In this system, a three-dimensional volumetric tessellation of the 3D object in question is created. The tessellation results in a number of finite elements which represent aspects of the object's physical properties such as toughness, plasticity, and volume. Once constructed, the finite elements are processed by a solver to model the stress within the object. The stress can be used to drive fracture, deformation, and other physical effects with a high degree of realism. Unfortunately, in the past, finite element-based systems had been impractical for use in games due to the performance overhead and lack of tools to create the necessary representations out of 3D objects. A primary limit of physics engine realism is the precision of the numbers representing the positions of forces acting upon objects. When precision is too low, small fluctuations not modeled in the simulation can drastically change the predicted results. Furthermore, simulated objects can behave unexpectedly or arrive at the wrong location. So, what happened before engines? How were games ever developed? Let's take a closer look. The term game engine arose in the mid-1990s, especially in connection with the 3D first-person shooters. However, before game engines, games were typically written as singular entities. A game for the Atari 2600, for example, had to be designed from the bottom up to make optimal use of the display hardware and the whopping 128 bits of RAM. Other platforms had more leeway, but when the display was not a concern, memory constraints usually sabotaged attempts to create data-heavy designs that an engine needs. Simply put, the tech just wasn't there yet. But game developers had other ideas in mind. Some went so far as to develop their own engines in-house that could run on the systems they wanted. While third-party game engines were not common until the rise of 3D computer graphics in the 1990s, there were several 2D game creation systems produced in the 1980s for independent video game development. Upon the release of id Software's Doom and Quake, rather than work from scratch, other developers licensed the core portions of their software and designed their own graphics, characters, weapons, and levels. The practice of licensing such technology has proven to be a useful auxiliary revenue stream for some game developers, as one license for a high-end commercial game engine can range from thousands to millions of dollars, and licensing has virtually no limitations with regard to the distribution of the actual software. As game engine technology matures and becomes more user-friendly, the application of game engines has broadened in scope. They are now being used for more serious games, visualization, medical training, and even military simulations. They're complex, they're powerful, and they're profitable. They are the beating heart of an entire industry. An industry so influential, it has even inspired professional competitions. From immensely chaotic firefights to simple structures, game engines enrich the lives of both developers and consumers alike. So the next time you sit awestruck while playing your favorite games, take a moment to appreciate what's really going on.